Hello, everybody. Today I'd like to continue talking about the Bayes theorem, and I'd like to show how it is used uh, in um, classification problems, even in machine learning type problems. Let's consider the following problem. We're a doctor, we have a patient, and the patient's sneezing and has a headache. We want to classify the patient into one or two categories. He has the flu or he does not have the flu. Now, from empirical evidence, we know what the probability of the flu is, the probability that you have both sneezing and headache when you have the flu, the probability you have sneezing and headache when you have no flu, and the probability of sneezing, the probability of headache. So we've got all that information. I think I may even have left a few out, but you can see how many things we know. That's not that hard to find. We base it on the number of cases we have, and we can just do a counting to estimate those particular probabilities. Well, how do we go about this? Well, we have the Bayes theorem. What we want to know is, well, we already have the probability of sneezing and headache given the flu. And from almost the definitions of probability, that is the probability of sneezing and headache and flu, the overlap of them, divided by the probability of flu. And the same thing is true the other way around. And as with all our Bayes work, there's a common probability in there. We set that common probability to solve for it in each of the problems, and we get this. And this gives us the same setup we've had before. The difference is that we're making a very big assumption, which I'll emphasize again in a minute. You'll notice that I've taken the probability of sneezing and headache given the flu, and instead put two probabilities together and multiplied them. That we'll talk about. Now you can do the same thing on the other side, and I basically did the same way. And now I'm going to talk about what I was doing there and how I made those changes. There are two simplifications we're going to use that will make it faster for us to do these. It takes a little while to do all this arithmetic. Sorry, I shook up everything that I shouldn't have. The first simplification is if you look at these two, the denominators are the same. Why should we bother calculating them or dividing by them? All we have to do is look at the two numerators. We'll compare the two numerators, and whichever one is larger, that's where we'll classify this patient. The next one is more controversial. This is the reason this is known as a naive Bayes classification. There are other Bayes classifications. The naive is that we're making an assumption that probably isn't true. We're saying that the probability of sneezing has nothing to do with the probability of having a headache. If we say they're independent, then there's no overlap. The probability of A and B can be taken as the probability of A times the probability of B. Now that's a big saving. We don't have to compute more probabilities of all possible things. And we're talking about cases where there might be 50 or 60 different qualities we're looking at to try to make our decision on the classification. So what I did was I substituted numbers. I hope I got them right. You know how I am with arithmetic. And I got that the flu was higher. Now, I'm going to try a case that will be very close, the kind of thing you're going to do for your homework. And this is closer to the way it's used in, say, machine learning. We're going to teach the computer something, or actually we're just going to give it a table and it can compute things from. And the table is going to tell us, going to list a lot of animals and say whether or not they give birth, whether or not they can fly, whether they live in water or not, and whether they have legs. And for each of those animals, we're going to say whether it's a mammal or not mammal. So there's, I think, 20 of them here, if I remember correctly. And, some of them I had a little trouble with, but we'll see what happens. What I want to do is I want now to have a case that is just the case I want to look at. I have an animal that gives birth, can't fly, lives in water, and has legs. What is it? A mammal or a non-mammal? That is the point of the classifier. That's what we're talking about. So let's look at how we might tackle this problem. What do we want? Well, we want the probability that we have a mammal given that we could put it in a loose form. We could say yn, yn. All that means is that we've answered these 4 questions as yn, yn. So we want that. Now, what do we have? Well, according to the formula back here, way back here, what I would like to have, now, I guess I better do it out right now. You see, I have P of something with these. Well, that equals P of the product of the union times the P of the thing I'm trying to get. So what I'm going to do down here now is I'm going to try to rewrite this. I'm going to say that this should equal P of Y. I better be more careful here. That gives birth. Birth equals Y, given that I have a mammal, times probability that can fly equals no, given, pardon me, I'm having some troubles with my keyboard. I'll get it in a second. Can fly equals no, given that we have a mammal. Given mammal times probability that the third element, live in water, is yes, equals yes, given that we have a mammal, and we got one more yet, times probability that have legs is no, given we have a mammal, and then we multiply that times the probability of a mammal. Now I'll put this in a little better form so that we can see the pieces here. I'll move this down here. Now, I'm sorry I didn't get it to stay on the same page, so let me get it on the same page. Now let's see if this looks like what we had before. Back before we had probability of A given B was the probability of each of these items given A times the probability of A. Where you see flu there, substitute mammal, and I think it'll work out. Where you see up here the 2 sneezing and headaches, substitute the 4 possibilities, and then you'll get these 4 multiplications. We only had 2 there, we'll get 4. Now, we also can go with a slightly, we can change that for the other half that we're going to be computing. We're also going to compute the probability of not mammal given all of those. So not mammal. And it's the birth here. We're just going to keep putting nots in. Not here. Not here. Not here. And I did that one wrong, pardon me. And I think that's the right one. 2 more to go. Not. Somehow I didn't do that, and this would be not. Those are the 2 things we're going to compute. Now I should be a little more careful. The equal sign isn't really correct there. What I should have is approximation, a wavy equal sign. It says that they're in the same proportion, but remember I threw away the denominators, so it's not an equal. Well, how in the world do I get all this stuff? I've got to find out all this information. Well, that's what I go to the table for. What's the probability that I have a mammal? Well, I'm only interested in the data set I have that trains the computer. I believe I counted 20 of these. And how many are mammals? 1, 2, 3, 4, 5, 6, 7. So that means there are 7 mammals and 20 cases. So I have 7 20ths. And it's easy enough to compute P of not mammal from that, because the sum's going to be 1. So mammal equals the 13 over 20. So we have that item. Now let's see, what can we get for birth Y given mammal? Now let's look back at the table. I want probability that Earth equals Y given I have a mammal. So I have a total of 7 mammals. How many of them have birth equal to Y? 1, 2, 3, 4, 4, so 4 to 1, and 5 to 1, but I must have missed one. There's 7, so let's do it again. 1Y, 2Y, 3Y, 4Y, 5Y, 6Y, and 1 no. So that's 6/7. Now, I can't do a subtraction there because I have to really compute from the table. But now let's go with birth of pi fly equals no, given that we have a mammal. Well, the denominator is going to be 7 again, but let's see what we get with the fly equals no. 1 no, 2 no's, 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1. Ooh, 6/7. Was that the same? I guess it was the same as the last one. Then we have the P of in water equals Y given mammal. Again, we have 7 cases, so the denominator is going to be 7. We have to see how many are living in water. No. So 1 so far. I don't know what that's supposed to be a no. So we have 1 so far. We have, I count 2. The dolphin and the whale. So it's 2/7. Now that's one. We got one more to go. We have to compute the probability that we have legs equals no given mammal. So again, the denominator is going to be 7. And how many of them have legs? Let's see. 1 has legs. 2 have legs. 3, 4, 5, 5/7. So I have 5/7. Now I think that's everything I need. I think I've just given you everything I need to take the first problem. So I think this. I don't know if I got that right. Let me do that once more. That equals, well, it's the 4 conditional probabilities times the probability of mammal. We have the 4 times the probability of mammal. So we have 6/7 times 6/7 times 2/7 times probability of a mammal is 7/20. Now I'm not about to try to compute that. I'm going to copy it. I'm going to go over to this area here. I'm going to have a new one, and I'm just going to put that in there. Then I'll take care of putting the equals in. So it equals 6/7 plus or times 6/7. And I probably will be super cautious and put in the parentheses. I don't want to take any chances. Times 2/7 times 7/20. 0.073. So we'll take that over. 0.073. So that is 0.073. Now we have to do the same thing for the other one. So we now have to take, we've got this part, that's no problem. So we'll take that down there. So we have C. Pardon me, I got it wrong. Take that down there. And I'll copy these and then we'll fill them in one by one. So I have those there. Now the denominator is going to be 20 in each case. Pardon me, 13. There are 13 non-mammals. This denominator is going to be 13. I'll get it sooner or later. And apparently one went off the page. So let me see if I can get it back. There it is. No, I guess I forgot to copy it. I have why I don't have birth. So I'll put that one in. And just to keep them in the same place, I'll put it here. And again, have the 13 here. And now we have to compute all the numerators. And remember that each of these is now a not. So I go over here and say not mammal. Excuse me. Not mammal. Here, not mammal. And here, not mammal. And here, not mammal. I try that one again. All right, so let's look. For the 13 non-mammals, how many give birth? So let's go through. No, 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 no. One so far. No, no. I count one. Maybe I'm wrong. I'll start again and look. None there, none there, none there. One there, the leopard shark. None there, none there, none there. I got 1 out of 13. Now, fly equal no, given not mammal. So start here. not. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'll just count the ones that do fly and subtract from 13. 1, 2, so I got it right, 11 13ths. Now, the ones that are in water, given not a mammal. So in water, given not a mammal. 1. I'm going to count that as yes. So we'll make that yes. I probably could make it half, but I won't. So I'll say 1, 2. I'm looking for what? In water or yes? Yeah, in water, yes. Pardon me. So not 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, I guess I should do what I did last time and count the no's. 1, 2. I got it wrong because I'm not going to get to 2. So let's try it again. Not mammal, and I want a Y. So far, none. Not mammal, I'll take the Y. Not mammal, I'll take the Y. That's 2 so far. I'll take the Y's from here, 3 and 4. I'll take the Y from there, that's 5, 6, 7. So it's 7 13ths. How did I lose? I guess I did. It's this one next. Looks like Y equals no. No, it's 7 13ths. I think I got that right, but let's make sure. Y equals no for not mammal. So this is the, oh, it was live water, pardon me. That was live water. And somehow I've lost the other one. I haven't lost it all. I got to bring it back up. Okay. Take it there. This one is the one I just computed. It was in water. And I have 2 more I can't seem to bring up. We'll see. I now have 1, 2, 3. I'm going to try one more. And apparently there's something here that's preventing it from coming up. So I'm just going to have to click here and that there. And I don't know what this thing is here, but it's going away. It's got to be a delete. Pardon me, I don't know why this is happening, but something is bothering me. All right, right here, I'm going to put have legs. That's what we want. And so I got to go back now and look at the not mammals and see which ones have legs. So look back at the not mammals for legs. No. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 13ths. Now I have one left. The probability of, I got the birth. Oh, I have the fly. Fly equal no, given not a mammal. So let's see what we got here. Not a mammal. So I'm looking at all the non-mammals and see which ones of them fly, do not fly. Okay. Not mammals. Well, 1, 2 do not fly. 3, 4 do not fly. 5 do not. 6, 7, 8, 9, 10, 11. I got 11 out of 13. And now it's very easy to compute what we want. The probability of not a mammal. A probability of not a mammal given a vector y, no, equals, and we multiply all these things together. 1/13 times 7/13 times 9/13 times 13/20. Now I think I copied everything down properly. There's 11. I missed one. There's an 11/13 there. 11/13 times 11/13 plus 13/20. There should be 4 of these. They're all there, and that one. So again, I'll take this over to the Excel. I'll type it there, and then I'll see what I get. So I have equal 1/13 times 7/13 times 9/13 times 11/13 times, that should have been a times, 13/20. It's complaining about something, missing parentheses, which I think it got right. No, didn't. Let me put back that parentheses where it's supposed to be. 13/20. And everything is right. 0.015. We can make it 0.016 if you want to. So 0.016 over here equals 0.016. We choose a mammal because mammal 1 up here, the mammal given these is 0.073. While the not mammal is 0.016. Now there, painstakingly, is the way to do it. I will not bet anything on whether I got those numbers right. It's more important that you saw how I did it and maybe can get the right numbers yourself. But it takes a double and triple checking, and I checked some of them, but I didn't check all of them. That is the naive Bayes classifier. Despite the fact that we are making an assumption that probably isn't true, it works. That's the way it is. It works. And what I've seen says it's fairly good. Now, I put this file out already, but I've just made some changes in it, so I'm going to put it out again for you. And along with that, there is another file out there that is the next homework. Here is another table of stolen cars. And you're going to feed that table in, and you're going to look at that table, and then you're going to try to find out, should you classify that car as being stolen? Is that true or not? Now remember, you're going to have to also classify car is not stolen, given same conditions. And you're going to have to pick out the one that's best. And that's it. I hope that everything works out for you. Again, this is not a program. You don't have to write a program. All you're doing is doing computation. Many places on the web have Python programs to do, that work with this, but you better be careful. The Python programs require pandas and skykit, so it's not probably what you did when you took Python. So I'll see you later. Bye now.